You have heard of software-in-the-loop testing, but do not know how to introduce this kind of system-level testing into your development? Don't worry, in this video I will explain the relevant concepts and show you an example of how to perform system-level tests of the software of an ECG device using Vector's Canoe tool and the SIL adapter. Hi, my name is Mario. I'm working in the Research and Development department at Vector and have been specializing in system-level testing, especially software-in-the-loop. In a previous video, my colleague Philip gave an extensive introduction to system-level testing for both the virtualized device, you might want to call it a digital twin, and the final hardware. I added the link to his video in the description. With our tool Canoe in combination with the SIL adapter or our Hill hardware, both software and hardware-in-the-loop tests can be easily added to your development. While it is easy to imagine how the device under test must be connected to the test hardware and test tool, it might not seem as straightforward for software-in-the-loop testing. Let me show you how simple it is to instrument your code to enable system-level testing early in development. Quick reminder, the ECG device that Philip has introduced in his video uses one input, the analog signal of the ECG electrodes, and two outputs. An alarm state that informs about unhealthy heart rates via I2C, and a connection to a patient monitor over Ethernet. The device is simple enough to be an illustrative example. One major advantage of software-in-the-loop becomes clear very quickly. It is not important what type of communication is used because we are only testing the application data that is being exchanged. For the ECG device, this is the ECG signal data and the calculated heart rates. Nonetheless, software-in-the-loop testing allows to check the intricacies of the complete core software or business logic on system level without the need for hardware. In a later step, hardware-in-the-loop testing also includes tests of the hardware-specific code, the hardware drivers. These hardware-in-the-loop tests can be performed during development on an evaluation board and as end-of-line tests of the final product. Feel free to take a look at exemplary tests for final hardware in our linked video. Through software-in-the-loop, high confidence in the software itself can be gained with early system-level testing. And due to the high reusability of test cases, almost no additional work is required. Imagine tests of the final hardware are performed, and some test cases fail. Without prior software-in-the-loop testing, it is impossible to locate the errors in the code. With successful testing of the core logic itself on system level, it can be safely assumed that the hardware-specific implementations or hardware integration-related issues must have led to the error. Adding software-in-the-loop testing to your development can also greatly reduce hardware integration times, saving you significant resources. The high reusability of test cases and the environment simulation between software-in-the-loop and hardware-in-the-loop is not necessarily given in every test tool. With the Vector test tools, Canoe and VTest Studio, this can be ensured, and software-in-the-loop can be easily incorporated into the development chain. Canoe enables communication and data exchange with the system under test in several ways. Hill hardware, such as the Vector VT and VIO systems, and Vector network interfaces are available for hardware access. The Vector SIL kit can be used for data exchange with a virtualized system. In today's example, I would like to focus on software-in-the-loop with the Vector SIL kit and SIL adapter, with simulations of the ECG pads, the alarm and the patient monitor in Canoe. In the software-in-the-loop example, ECG signal data is sent to the system under test, and the test tool expects to receive the calculated heart rates and the alarm state. Keep in mind that all data is directly transmitted between the test tool Canoe and the running executable of the ECG application. This means that it is irrelevant that I2C and Ethernet are the chosen transport protocols in the final product. Because it is impossible to write the code of a functional ECG device in a few minutes, I will start this example with the C++ code of the final device, including the relevant algorithms for heart rate calculation and the hardware-specific code. As Philip has already shown in detail, it is advantageous to have a clear separation of hardware-specific code and the core logic, with an I/O abstraction layer in between. Here, we have three CPP files, logic.cpp with the core algorithms, IO.cpp with the I/O abstraction layer, and hardware.cpp with the hardware-specific code to read from and write to physical I/Os. The idea of the instrumentation of code for software-in-the-loop testing is to exchange the implementation of, for example, hardware.cpp to use the SIL adapter to exchange data with the environment. the SIL adapter uses Unix sockets for communication instead of the protocols I2C and Ethernet as in the real device. In this example, I will use CMake. CMake cache variables allow to easily switch between the two code bases, as you will see. Now let's dive into the code and Canoe. Here we can see the graphical interface of Canoe with the graphics window that shows the data that is being exchanged with the system under test. We can see a simple panel to start, for example, the curve simulation from the patient data, and we can see the trace window again displaying the data that is being exchanged with the system under test. The variables or the data that is being exchanged with the system under test is defined in the VCDL file. If we take a look, we can see that here we have a namespace, SmartECG. Within this namespace, an object SmartECG.io is being created, and it contains the variables of the O members, ECG amplitude, current heart rate, average heart rate, and heart rate alarm on. The ECG amplitude is a provided data, which means Canoe sends it to the system under test, while it receives all of the consumed members. What we want to do is we want to create the SIL adapter from this VCDL file. To do so, we can use the SIL adapter builder, which is contained in the installation folder of Canoe. So if I start this executable, which is located in my case in program files, vector Canoe family 18, 18.3.118, XX64, and then we have the executable SIL adapter builder. As an argument, it needs the location, the path of the VCDL file, which in my case is in the SIL workshop, Canoe, VCDL, and smartecg.vcdl. As optional arguments, we can give the output folder where the SIL adapter is being generated to, so the CMake project. In this case, I just want to be the current folder, the SIL workshop, and I can specify the language of the SIL adapter. In our case, I want to use a C++ project, so CMake project, so I just give CPP as the parameter. Now the data model is being retrieved and validated, and as a next step, the SIL adapter is being generated purely from this VCDL file. We don't need to define anything else. So the generation of the SIL adapter was successful, and we can now take a look at what actually is contained in this folder. We have the folder Canoe with the Canoe configuration that you can see in the background and that I have shown in the beginning. We have the folder SUT with the system under test, as well as the build SIL adapter and this folder siladapter.build. Within the folder SUT, we can see that we have the folder components with libraries that we are using, for example, for the heartbeat detection algorithms. And in the folder main, we have the files that I've mentioned earlier, main.cpp, logic, IO, hardware, and so on. As you can see, we have everywhere these CMake list files. So we already have a CMake project running. What we want to do now is create a new CMake project which uses the CMake project of the system under test as well as the SIL adapter. To do so, we create a new file, CMake lists.txt. And now we can start using Visual Studio Code to change or to generate this the CMake project. So what I want to do is I need to specify some things for CMake to run. For example, CMake minimum required, which is just an arbitrary version that I set here at 3.10. I create a project. I call this ECG, and I give it a description, which is, in this case, SIL tutorial. What I want to do now, as I said earlier, I want to create a CMake cache variable. because it allows us to change between building for the final device, hardware in the loop, or for this software in the loop case. So I create this option. I call this option build for SIL. Again, I give it just a short description, build with SIL adapter, and I give it the default value of on. What I want to do is add the subdirectories system under test. I want to have this both when HIL and SIL is being generated or built, and I want to add the subdirectory SIL adapter, but only in the case when I'm building for SIL. So I'm checking if build for SIL, then I want to add the subdirectory SIL adapter. I can save this, and the build files have already been written to the folder build. The configuring and the generating has been done successfully. Now, what I need to do is change the CMake lists of the system under test, because as you can see here, we're always using the implementation currently in hardware.cpp. As I've said earlier, I want to exchange this with a new content. So what I want to do, in the case that I'm building for SIL, so this cache variable is set to on, I want to have the target source be something different. I will set this in a second. And in the other case, which is the case I want to build for hardware in the loop, I want to have the target source for this application be main hardware.cpp. So now I can remove this hardware.cpp from this content here, because I only built this or use this implementation in the hardware in the loop setup. In this other setup, I want to use a new implementation. And I want to call this file sil.cpp. Additionally, I need to link this SIL adapter library. Again, to the application. Now what I need to do, obviously, is create the sil.cpp. What I want to do in the sil.cpp file is implement hardware.h, identically to how hardware.cpp implements hardware.h. So I will copy hardware.h, paste it into the same folder, and rename it to sil.cpp. Now I can also save this file because the file exists and the generating is being done again. So in sil.cpp, what I want to do as a first step is just generate empty implementations. I want to include hardware.h, and I want to exchange out of these semicolons as a quickest means with parentheses. And for this function, because it returns an integer, for now I will just return 0. Because it might take a while, I will build this very quickly, and in the meantime show you the code that is currently already existing. Within the main function, as a first thing, we print a welcome message. This could be a display on the ECG device. We reset the detection algorithm, and we initialize the IOs, which means registering callbacks, hardware interrupts to read ECG input, in this case every 5 milliseconds for the hardware in the loop case. And then we just keep the main thread alive by sleeping in a loop. In logic.h, we only have one function, read and evaluate ECG sample. It's a rather simple program. And in logic.cpp, we can see that this function calls another function, evaluate ECG sample, which has as a parameter the return value of the function read ECG sample. Read ECG sample is defined in io.h, as you can see here. And in io.cpp, all it does is call a function that is declared in hardware.h. If we take a look at the implementation, hardware read ECG sample, we can see that analog to digital converters are being used, and we can see that it's an ESP microcontroller specific function that is being called here. To send data, we're using I2C, so we have a hardware specific I2C specific implementation, as is expected in the case of the hardware-in-the-loop setup. Now that the build has finished, I can implement the SIL adapter into this new file sil.cpp. Obviously, I need to include the SIL adapter. I can use the SIL adapter now to connect. Let me quickly do this so the squiggly line disappears. I have to connect the system under test with Canoe. This is rather simple. I only need to call the function vector Canoe SIL adapter connect. Now, when the function hardware init is being called, the system under test, or the SIL adapter within, connects to Canoe. For the hardware shutdown, we can do a similar thing. Instead of calling the function connect, we call the function disconnect. Now the interesting part happens. How do we get the variables, the data from Canoe, in this case the ECG data, to the system under test? And I will open the VCDL file. In parallel. And as I've said earlier, I have the variables within the namespace smart ECG, the object smart ECG IO, and we want to have the variable ECG amplitude. So all we need to do is return in the namespace smart ECG, the object smart ECG IO, and the variable ECG amplitude. This is everything that you need to do to exchange data from Canoe to the system under test. Within a few minutes, I've been able to connect the two and exchange data. To send data back from the system under test to Canoe, all we need to do is write to these variables. So smart ECG IO. In this case, we want to send the current heart rate. And we just set it to the current heart rate, which is given as a parameter in this function. So let me close the VCDL file just so that we can see better what's happening in the system under test. For the average heart rate, it's exactly the same thing. Smart ECG IO, average heart rate is being set to the average heart rate that is being given as a parameter to this function. The same thing for the alarm. So if we want to print a status, could be a display on the ECG device. Here we want to use a terminal, just for debugging purposes. So I just call the function printf. I say peak detected, and I just print the averaged heart rate and the alarm state. And here, obviously, I want to print the average heart rate and the heart rate alarm on, given as parameters to the function. For the welcome message, the only thing I want to do, again, here printf application started. and the hardware loop sleep. In this case, I just want to use the Windows sleep function, so I need to include windows.h. Now, there is one thing missing. In the hardware in a loop case, we're using hardware interrupts. Here, there are no hardware interrupts implemented yet. So what we can do is register update handlers. So whenever a variable is written in Canoe, a certain function is being called in the system under test. The function that we want to call is read and evaluate ECG sample. This function is declared in logic.h. And we want to do this during the hardware initialization step. And we want to do this when the variable ECG amplitude is being written to. In Canoe, who's the time giver, we do this every 5 milliseconds. So this is exactly what we have in the hardware in the loop case. So whenever the variable smart ECG IO, ECG amplitude is written to, we want to register an update handler for this variable. And here we just want to call the function read and evaluate ECG sample. We can save the file, build. Now that the build has finished, we can run the application. We are immediately greeted with the welcome message, application started. Now we can also start the measurement in Canoe. And we can immediately start the ECG curve simulation from the patient data. In the system under test, we can see at some point that peaks are detected and heart rates are being calculated. Switching back to Canoe, we can now simulate an emergency. This means we switch the data set for the ECG signal. We can see that the heart rate alarm is being turned on. We can also see this in the system under test. If we now stop the emergency, switching back to the initial data set, we can see that after a certain time, as soon as the average heart rate reaches a value below 100, the heart rate alarm is off. And we can also see this in the system under test. Now, this has taken a while. We can also automate these steps and write automated tests. With software in the loop, we don't need to do this in real time, also run these tests in real time. We can speed up the process. To do so, I will stop the measurement, switch to a factor, and speed up the time by 100. Now, when I start the measurement and start the ECG curve simulation, everything happens much more quickly. We can again see this in the system under test. The automated tests can be run from Canoe, and we get the immediate feedback that every test has passed. That's all for today on SIL testing. Now get in touch to talk about your SIL use case. Further links are in the description below. Thank you for watching. There are many more interesting tutorials on HIL and SIL testing, Canoe, and other topics on the Vector Tech tutorial channel. Subscribe now and activate notifications to not miss new videos.